Section: Introduction. In this section, we discuss the challenges associated with large language models, LLMs, and their tendency to generate hallucinations. These hallucinations can occur due to factors like complex models, flawed data sources, or random sampling. The trade-off between deterministic decoding and creative sampling methods can increase the likelihood of hallucinations. However, understanding and detecting these hallucinations is crucial for improving LLM performance. To address this issue, we introduce HalluciBot, a novel model that predicts the likelihood of hallucination before generating any output for a given query. HalluciBot provides a binary classification indicating whether a query is prone to hallucination or not, as well as a multi-class hallucination rate estimation. By leveraging a multi-agent Monte Carlo simulation, HalluciBot is trained to quantify hallucinations effectively. Our study has led to significant contributions, with HalluciBot achieving a validation accuracy of 73% for binary labels and top 3 multi-class labels. Unlike existing methods that detect hallucinations during or after user sessions, HalluciBot's approach reduces computational waste by conducting sampling and training beforehand. This makes it suitable for various systems, including those with retrieval augmented generation, RAG, context or few-shot question answering systems. Furthermore, our experiments have uncovered behavioral and statistical insights, such as ILM's tendencies to be either highly accurate or completely incorrect in certain scenarios. We have detailed these findings in our appendix. Previous research has primarily focused on post-generation analysis to mitigate hallucinations, with limited emphasis on pre-generation strategies. HalluciBot's unique approach of combining multi-agent modeling with query perturbations sets it apart from existing methods and enhances its effectiveness in detecting hallucinations. Section Summary. In this section, we introduce the concept of hallucinations in large language models, LLMs, which can arise due to factors like model complexity and flawed data sources. We highlight the importance of addressing hallucination issues through methods like post-generation output analysis and propose HalluciBot, a novel model that predicts the likelihood of hallucination before generating any output. HalluciBot leverages a multi-agent Monte Carlo simulation to quantify hallucination rates, achieving a validation accuracy of 73% for binary labels and top 3 multi-class labels, offering a proactive approach to mitigating hallucinations in LLM-generated content. Section: Methodology Overview. In this section, we will explain what hallucination is and how it relates to large language models, LLMs. Hallucination occurs when LLMs produce outputs that either directly contradict the original content or are irrelevant. There are 2 main types of hallucinations: intrinsic, where the LLM's outputs contradict the source content, and extrinsic, where the outputs are unrelated to the source. Additionally, factuality hallucinations involve outputs that are false, while faithfulness hallucinations involve outputs that misunderstand the query's context. We will focus on these types of hallucinations and introduce a new concept called truthful hallucination. Truthful hallucination occurs when an LLM can't answer queries that are similar but phrased differently, revealing a bias in its training. Our goal is to address this issue with our HalluciBot system. HalluciBot aims to quickly predict hallucination in LLMs before generating outputs. Unlike previous methods that rely on multiple generations to ensure consistency, our approach focuses on empirical estimates rather than model uncertainty. We use a multi-agent simulation, which is different from the usual single-agent experiments. To understand truthful hallucination better, we introduce the query perturbator, which generates variations of a query to uncover any training bias. The output generator then produces multiple outputs for each perturbation to mitigate the risk of bias from the LLM's training data. This process ensures independent output generation for each query variation. Section Summary. In this section, we delve into the methodology overview, focusing on the concept of hallucination in LLMs. Hallucinations are categorized into intrinsic and extrinsic types, as well as factuality and faithfulness hallucinations. We introduce the novel concept of truthful hallucination, which highlights the neural network's tendency to memorize training data and their inability to answer semantically similar but lexically different queries. Section: What is the purpose of a Monte Carlo simulation in HalluciBot? In this section, we aim to understand the purpose of a Monte Carlo simulation in HalluciBot. We have observed from various studies and Section 3.1 that hallucinations result from multiple factors, making it challenging to find a straightforward solution to model them. Therefore, we utilize a Monte Carlo simulation to obtain practical estimates of hallucination rates in LLMs. This method is commonly used to analyze probabilities when dealing with random variables. Our goal is to estimate the likelihood that a query leads to hallucinations. After completing the Monte Carlo simulation on our training dataset consisting of 369,837 queries across 13 different datasets, we proceed to train our classifier. These queries cover scenarios like extractive, multiple choice, and abstractive, each of which can influence the hallucination rate of GPT 3.5 Turbo. The estimates obtained from the Monte Carlo simulation are linked to an approximation of hallucination rates. By using a set of synthetic labeled queries Q_0 and their corresponding hallucination rates P_H, Q_0, we train an encoder-style classifier based on BERT and RoBERTa. We create two models: a binary model to predict if a query might cause hallucinations, and a multi-class model to estimate the expected number of hallucinations after sampling n+1 times. Our experiments limit the number of perturbations to n=5, allowing us to model hallucination rates for n+1=6 scenarios, representing a 16.6% increase in hallucination rates. We investigate how different scenarios affect hallucinations by conducting an ablation study. By adding tags like extractive, multiple choice, or abstractive to the original query Q_0, we aim to reduce hallucinations. This approach is inspired by recent research suggesting the use of RAG to mitigate hallucinations. Additionally, we apply this technique to differentiate our findings from reused datasets in various scenarios, such as SQUADV2. The queries are encoded exactly as they are in the original datasets. To empirically estimate the probability of truthful hallucinations for a query Q_0, denoted as P_H, Q_0, we analyze the output A_I from our multi-agent Monte Carlo simulation using an indicator function I to measure incorrectness compared to the ground truth Y for the query Q_0. We simplify the assessment of hallucination propensity by defining binary values for the probability of any hallucination as P_B, Q_0. HalluciBot is trained to predict the occurrence of hallucinations under n+1 trials by converting the original estimate P_H, Q_0, into discrete classes multiplied by n+1, denoted as E, P_H, Q_0. Section Summary. In this section, we utilize a Monte Carlo simulation to estimate the probability density of inducing hallucinations in LLMs due to the complexity of confounding variables. After completing the simulation on a training corpus of queries, we train a classifier using BERT and RoBERTa to predict hallucination probabilities, distinguishing between binary hallucination occurrence and multi-class hallucination estimates based on the number of trials. Incorporating different query scenarios and additional context helps mitigate hallucination rates, with extractive scenarios showing lower rates and abstractive scenarios displaying higher disparities in correctness. Section: Metrics for hallucination. In this section, we examine two main metrics for evaluating hallucination: accuracy and agreement. Accuracy focuses on how correct individual agents are in their generated outputs compared to the ground truth. We use a matching approach that allows for partial and case-insensitive comparisons to assess correctness. If the output does not match the ground truth, we assign a score of 1. Otherwise, it's 0. We also look at the agreement among agents by considering statistical measures like item difficulty, Fleisch's generalized kappa, mean certainty, and Gibbs's M2 index. These measures help us understand how much the agents agree on their responses, regardless of correctness. To ensure the reliability of our simulation at the corpus level, we use Cronbach's alpha statistic. Our experiment covers 13 datasets divided into 3 scenarios: extractive, multiple choice, and abstractive. We use various datasets like SQUADV2 and Truthful QA to evaluate different aspects of our model. Our Monte Carlo simulation involves 2 components: the query perturbator and output generator, both based on GPT 3.5 Turbo. We maintain consistency in parameters across all agents. To evaluate the grammatical correctness of the generated queries, we use a Roberta model trained on the Google Query Well for Medness dataset. Our training setup utilizes Hugging Face's trainer class with the Atom Optimizer on an AWS EC2 instance with a single GPU. We fine-tune BERT and Roberta models, addressing label imbalance with a weighted loss approach. The train, validation, and test splits align with the original dataset divisions, with specific sample distributions outlined in our tables. Section Summary. In this section, we introduce 2 key metrics, accuracy and agreement, to evaluate hallucination. Accuracy is crucial for assessing individual agent truthfulness by comparing generated output to ground truth, while agreement measures correlation. We also analyze reliability at the corpus level and use statistical measures like item difficulty and Fleisch's generalized kappa to evaluate agreement among agents. Section: Aggregated Monte Carlo results. In this section, we present the combined results from our Monte Carlo simulations. These results show how different question-answering scenarios perform relative to each other. On average, we found that extractive answering performs better than multiple choice, which, in turn, performs better than abstractive when faced with changes. This trend suggests that the performance of GPT 3.5 Turbo is affected by having more content available. Abstractive tasks show the most variation in agent responses under changes, emphasizing how adding context helps reduce incorrect answers. Detailed results can be found in the tables provided. When it comes to extractive question answering with context, GPT 3.5 Turbo does well on the SQUADV2 dataset, with high accuracy and agreement among the agents. Even when faced with significant changes, keeping the context unchanged helps the agent give correct answers consistently. For multiple-choice question answering, having answer choices available reduces incorrect answers when faced with changes. The combined accuracy of multiple agents is slightly higher than the baseline, showing that using multiple agents can improve accuracy rates to some extent. In abstractive question answering without additional context, GPT 3.5 Turbo achieves moderate accuracy under changes. There is a notable difference in the rates of incorrect answers compared to other scenarios, with significant variations across different datasets. For example, the SQUADV2 dataset shows a considerable decrease in accuracy compared to its extractive counterpart. However, there are benefits in this scenario, leading to an increase in accuracy as the likelihood of generating a matching answer rises. Our analysis reveals that the changes made by GPT 3.5 Turbo are consistently coherent, with a high well for Medness score. In contrast, the original queries show a decline in well for Medness score, indicating less coherence. Detailed results and sample changes are provided in the tables. In terms of binary results, the best HalluciBot achieves high validation accuracy and F1 score. With fine-tuning, the F1 score improves further. For multi-class results, HalluciBot achieves good validation accuracy and top 3 accuracy. Including the scenario in HalluciBot's prompt has proven to be beneficial in distinguishing similar queries with different contexts. This inclusion leads to significant improvements in F1 score for binary cases and accuracy rates for multi-class validation. The testing set presents challenges such as the absence of extractive samples, an overrepresentation of multiple-choice queries, and a different distribution of labels compared to the training and validation sets. Therefore, we rely on the validation results for our analysis.